Good morning, my chemistry students. Today we are continuing with our Unit 2 lessons. We are actually starting the bonding content of the unit. Don't fret, nomenclature is not going anywhere. We'll actually keep coming back to it throughout the rest of the course. But today we're going to take a little break from it. We are looking at Standard 2 today. Specifically 2D, where we're looking at bonding configurations. And we're also talking about properties of our ionic and covalent compounds. So I actually want to start with something that's a little bit of a review from Unit 1. If you remember back in Unit 1, we actually learned about our intermolecular forces. So those were the attractions between molecules. And we learned about intramolecular forces. Our intramolecular forces were the attractions between atoms. Those were our bonds. And in Unit 1, we actually learned about 3 types of bonds. We learned about that ionic bond, which forms due to the transfer of electrons. And we saw that the ionic bond is typically between a metal and nonmetals. And there is an illustration of an actual ionic bond forming. We've got that metal losing an electron to form its cation, and the nonmetal gaining an electron to form the anion, and opposites attract. So that positive and that negative forms an extremely strong attraction. We also saw that covalent bonds were formed due to the sharing of electrons. They form between elements that have very similar electronegativity values, where ionic bonds actually form between elements that have larger differences in their electronegativity values. Covalent bonds form between typically 2 nonmetals, but we do see metalloids and nonmetals forming those covalent bonds as well because their electronegativity values are still extremely similar. Now, we did see 2 types of covalent bonds, and we will actually talk a little bit more about these 2 specific types of covalent bonds later in this unit. And we are looking at that nonpolar, where the electrons are shared equally. And we are looking at polar, where the electrons are not shared equally. So you've got a larger difference with your polar bonds and basically almost no difference in their electronegativity with the nonpolar. But the thing I wanted to kind of focus back on is the fact that ionic, we're transferring electrons, covalents, we're sharing. And yes, we did see a third intramolecular force back with Unit 1, and that was our metallic bonding. And metallic bonding occurs within just metals. So this isn't a compound. These are just pure elemental metals. And that metallic bonding, remember, is that sea of electrons. The electrons kind of spread out amongst all of the metals, and they're shared between them all. That's what gave metals their physical properties. Excuse me. So that's the reason why our metals are able to conduct electricity. That's why they're able to be pulled into wires. They're ductile. And that's why they're malleable. They're able to be pounded into shapes because of the sea of electrons that are in there. They're not sharing electrons. They're not transferring electrons. It's just the electrons are amongst all of them. And this is just with plain solid metals. Now, back in Unit 1, we talked about the strength of these compounds. And the strength of these compounds kind of give us a clue as to the physical and chemical properties of specifically our ionic and covalent compounds. Because this unit is about nomenclature and bonding, we're looking at those ionic and covalent compounds and the properties that they form, or the properties that they have when those compounds form. So notice that my ionic bond is the strongest type of bond possible. This is the strongest attraction that is out there, with my covalent being considerably weaker. Now, the reason why that ionic bond, or my ionic compounds, have such a strong bond is due to the fact that it's formed from those ions. That positive cation, where did my thing go? And my negative anion, that attraction is what gives it its strength. So we've seen as we've been writing the chemical formulas for these compounds that they're neutral. Even though they're made of ions, the ions themselves cancel out. That's why when I have something such as calcium, who has a +2 charge, bonding with chlorine with a -1 charge, that compound would end up with 2 chlorines to balance out that 1 calcium because it is overall neutral. This is the compound on the right side. I'm going to put a blue box around it. That's the chemical formula. And it is extremely, extremely strong bond. So because those electrons are transferred from the calcium to the chlorines, it is it's a strong bond. I don't know how many ways to say it. Transfer of electrons result in very, very strong bonds. Now, if we were trying to look at this in terms of what's actually happening at not quite the exact atomic level, but at the valence electrons level, we can actually see our metals give up their electrons. So we would see that sodium, for example, would give it to chlorine. And that means chlorine ends up with that extra electron over here. So we can kind of see it now has sodium's little electron and it now has a negative charge. That attraction is what forms that extremely strong bond. So, and remember, since this is a binary compound, its name ends in "ide." So that thing's called sodium chloride. So different examples, but same idea. We can see that magnesium has its 2 valence electrons. Remember, my valence electrons we know by our group number. And magnesium is going to give both of these electrons over to the sulfur. And we would see that sulfur ends up having that full octet. Magnesium has dropped down in energy level. It still has valence electrons. It's just we're not showing them because it's an energy level less. And that positive and that negative attraction, we end up with 1 of each. So my chemical formula would be MgS. The name would be magnesium sulfide. But that positive and that negative attraction that we are trying to illustrate on the right side of the screen is that extremely strong bond. And that extremely strong bond is what gives ionic compounds their properties. So throughout the course, I've been referring to them as ionic compounds, but they also are called another name. Ionic compounds are also called salts. So when a chemist says salt, we don't just mean the stuff that you put on your French fries. We mean any ionic compound. So for example, if you've ever used Epsom salt, Epsom salt is something that you can soak in if you get, sore muscles. Many athletes kind of use it if they've gotten banged up or bruised up for a day. Well, Epsom salt is magnesium sulfate. And you would not want to put Epsom salt on your French fries because it would result in probably diarrhea because it is a diuretic, not a diuretic, a laxative. Sorry, wrong word. But it's still salt. Of course, yes, sodium chloride is a salt, but it's not the only salt out there. So like aluminum chloride is also a salt. All ionic compounds are called salt. And they all form due to that transfer of electrons. And because the electrons have been transferred, they are an extremely strong bond. Now, our ionic compounds, we've seen this with nomenclature, ionic names and formulas, all start with a metal. So ionic compounds involve metal at the very beginning, and then we've got our non-metal or our non-metals, our polyatomics at the end. Now, when we see ionic compounds, they are always solids at room temperature. So if they're sitting out on the countertop, they're going to be a solid. They have extremely, extremely high melting and boiling points. There are very few that you can actually melt at home. Most of them require close to thousands of degrees, if not higher, to melt. But if you were to take table salt, for example, and put it in a pan and put it in the oven, you would not be able to melt it. Not going to happen because that bond is so very, very strong, let alone boiling points. Now, an interesting thing about most ionic compounds, when they are dissolved in water, will conduct electricity. And this is actually really, really interesting, but it's where we get the term electrolyte. So those of you, when you're drinking that sports drink and you're drinking it so that because it has those electrolytes in it, well, that electrolyte is just a salt that is in your drink that allows your brain to conduct an electric current. It doesn't give you energy. It just lets your brain and your body conduct electricity, which is needed for your brain and your muscles to communicate and function properly. So electrolytes are something that can conduct electricity. And specifically, our ionic compounds do form electrolytes. Now, when we're looking at our ionic compounds, this would be some examples of what they look like. I've got two that are just straight up images. This top one is a really, really, really pretty crystal. I can't remember the exact one it is, but I do remember that this bottom one, it's different. It is our sodium chloride. And each one of those little boxes is not an individual sodium chloride thing. It's kind of groups of atoms. So if I were to take one of these boxes and zoom in, it would look like this illustration here. And we can see that in that ionic compound, we have alternating sodium atoms and alternating chlorine atoms. Now, how did Miss Raines know that the purple one? Actually, I did that wrong. The purple one is not sodium. The purple one is supposed to be chlorine. And the reason I know it's chlorine is because back when we learned about our periodic trends, we saw that in the same period, our element size decreases. So that chlorine ion, well, chlorine atom is smaller than sodium atom. Our ions have similar patterns. So covalent bonds, they cooperate, if you want to think of it that way. They cooperate and they share their electrons. Because they're sharing their electrons, they have considerably opposite properties of ionic. So we kind of got picked two groups of compounds and two groups of properties that we need to know. Covalent bonds, they share their electrons. And primarily we deal with binary compounds. We deal with our diatomic elements, basically things that have two atoms. But I do like to show that not everything that's covalent has just two atoms. So the illustration at the bottom of the screen is actually an atomic picture of caffeine. And I don't know about you guys, but some days I can't live without caffeine. Well, caffeine is a very, very, very large covalent molecule. All of those atoms are held together by sharing electrons. And they share their electrons in order to get that octet, but they also share their electrons because they have very similar electronegativity values. So my ionic bonds form by transferring electrons to get their octet, covalent share. Now, since my covalents are sharing and they're cooperating, they do have very different properties. Covalent compounds also have another name. They are called molecular compounds, or they are called molecules. You might remember this from biology when you learned about the water molecule. So molecule is just saying that it's covalent. You will have me using the terms molecular, molecule, and covalent all interchangeably. Same with our ionic. I will use the term ionic and salt interchangeably. Now, the nice thing about our covalents is there's no metals. So we're looking at predominantly two or more nonmetals. Yes, we know that our metalloids can form covalent bonds. So 99% of the time, our metalloids and a non-metal are a covalent bond as well. Those covalent bonds we're sharing those electrons again, and they are considerably weaker. So because the bonds are considerably weaker, they have much lower melting and boiling points. Most covalent compounds are either liquids or gases at room temperatures, but those that are a solid are not a very strong solid. They're a weak solid. So I don't know if you've ever played with Crisco or seen, like bacon fat. Once it's at room temperature, it's just kind of like goo. It's a solid, but it's gooey. Well, that has a bunch of covalent bonds in it. It's a bunch of carbon and hydrogen bonds. Now, most of them are liquids or gases, and that means they have considerably lower melting or boiling points because they've already melted at room temperature. They are not a solid. If you're wanting to get a solid covalent compound, most of them you have to cool down. So think about water, for example. In order to get it to turn into a solid, we got to freeze it and it becomes ice. But they do have, even those solid covalent ones do have very, very low melting boiling points. Chocolate can melt in your hand. It is a bunch of covalent bonds. Now, the neat thing about covalent bonds or covalent compounds is they don't conduct electricity, because when I put them in water, they do not separate into ions, so there's no way to conduct electricity. So they are considered non-electrolytes. Non-electrolytes do not conduct electricity. Electrolytes do, and we were specifically talking about being dissolved in water. So I can't run electricity through a block of salt, but I can run electricity through salt dissolved in water. Now, in terms of our properties, that is basically it. You're going to need to make certain you recognize what property goes with which type of bond. And if you just remember their strength, you've kind of got it situated. So ionic has those stronger, harder, higher properties, where covalents are the weaker ones. Excuse me. Now, with covalent compounds, we do have some additional terminology that I wanted to at least introduce today. And that is how we describe types of covalent bonds. Let's see if I can, nope, that's not what I wanted to do. You know, when I don't want to hit it, I hit the button, and when I do want to hit it, I don't hit the button. So notice in my nice pretty picture down here of caffeine, we've got these lines. We've got single lines, we got double lines, and yes, we can have triple lines. This particular illustration doesn't do a great job of showing all the little lone electrons that are left over, but my diatomic element on the right-hand side of the screen does show it. It does show those electrons that are left over, and we're showing that shared pair in the center.